All right, y'all, today we are going to continue learning derivatives of special functions. We are going to go over the derivatives of the remaining trig functions. So make sure you get these in your notebook. They are important for you to know, and you should have them memorized. Okay, so as a reminder, the derivative of tangent x is secant squared x, which is the same as like writing secant x squared. That means the same thing, but in calculus we're going to represent it in this way. And then if you were to use the quotient rule, and the fact that cotangent is the same as 1 over tan x, if we use the quotient rule and that information, we could get to the derivative of cotangent. I'm not going to prove the derivatives because we don't really have time for that. So I'm just going to have you write down what the actual derivatives are, but they come from the quotient rule. Okay, so go ahead and write down the derivative with respect to x of cotangent x equals, and remember we made a note, the derivative of cos are negative. This is a co, so we know this derivative is going to start with a negative, and then it's kind of related to the derivative of tangent. The derivative of cotangent is negative cosecant squared x. All right, so you can see how those are kind of similar, secant squared x versus negative cosecant squared x. So that can help you memorize them. They're kind of related, derivative of tangent and cotangent. Let's move on and go to the derivative of secant and cosecant. All right, so the derivative of secant x, derivative of secant x is secant x tangent x. So it's actually two trig functions multiplied. Derivative of secant x is secant tangent. And then the derivative of cosecant x, it's a co, right? It's a co, so we know the derivative is going to be negative. And then it's kind of related to the derivative of secant. It's similar. The derivative of cosecant is negative cosecant x cotangent x. So you can kind of see the similarities here. Secant, cosecant, tangent, cotangent. All right, so hopefully that helps you memorize those. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. Okay, now let's do an example with these, or a few examples. So the first one is we're taking the derivative of secant tangent. Not to be confused with the derivative of secant. The derivative of secant is secant tangent, right? But we're trying to take here the derivative of secant tangent. Notice that this is two functions being multiplied. So what rule should we use when we take this derivative? The product rule. We need to use the product rule. So we're going to do the derivative of the first. Remember, this is the first, times the derivative of the second, plus the derivative of the second times the derivative, times the first. Okay, so here we go. Derivative of the first. That is secant tangent. Derivative of secant is secant tangent. Times the second, so now I just do times, I'm going to do times with my parentheses, times the second is tangent x. We're not taking any derivatives, we're just multiplying by the second function. And then plus the derivative of the second, derivative of tangent is secant squared x times the first. Well, what did we start with? What was our first? Secant x. And then you could simplify, you could factor. So let's just like really quick notice how we can do those things. So if we simplified this, we would get secant x and then tan squared x, because we have tangent times tangent. And then we have plus secant cubed x. And a lot of time in calculus, it's going to be helpful to factor out a GCF. So let's really quick make sure we recognize that we have secant as a GCF. So you could also write this as secant x times, and then we have tan squared x plus secant squared x, because we took one of those secants out, divided by one of them. Okay, Let's go ahead and continue. So now we're going to do this derivative. I want you to try first, and then we'll do it together. Go. Okay, so again, we have a product. We have a product. Cosecant x times cotangent x. This is your first function. This is your second function. And we're finding y prime. So we would say y prime equals derivative of the first. Derivative cosecant is negative cosecant x cotangent x times the second. So that's times cotangent x plus derivative of the second, derivative of cotangent is negative, cosecant, negative cosecant x times the first, or sorry, derivative of the second, yeah, times the first, so times cosecant x. Sweet. And that is our derivative. And if we wanted to, we could simplify, just like we did in the first one, right? Some of y'all have asked me about this positive negative situation. So like you're multiplying positive times a negative. So you could just write this whole right-hand term, this whole thing, you could write as negative. So I can show you that. This is the same as, I'll simplify this one. Negative cosecant x. We have cotangent squared x. And then minus, because the positive times the negative, cosecant squared x. Cool. And we could factor out a GCF if we wanted to, but no need right now. All right, let's do a couple more. What if f of x equals tan x over sine x? Well, what do we have here? It's not a product rule, but we have a quotient. Division. That means we need to use a quotient rule. So remember, we're going to use that low d high minus high d low over low low. So let me label low and high. And let's go ahead and write f prime of x equals, okay, we're going to do low. So just copy the low, sine x, d high. So that means derivative of tangent x, which is secant squared x, plus high, that means copy the high, tan x. Oh, sorry, minus low d high minus high times d low. So derivative of sine is cosine x. All over low, low, so low squared, that would be sine squared x. Cool, and there's our derivative. You try this one, and then we will do it together. Go. All right, so again, we have a quotient, and so we have a high function, a low function, and we're going to do low, d high, so low is cosine x, d high is the derivative of cotangent x, which is negative cosecant squared x, minus high d low, so copy high, cotangent x, then multiply by the derivative of cosine x, because that's the low. Derivative of cosine is negative sine x, all over low, low, which would be cosine squared x. And that would be our derivative. Again, this negative, and this negative would multiply and turn the numerator into a positive. So just be very aware of your signs. And it's safe to like every time you plug in, put parentheses around what you're plugging into. That's like the safest way to do these rules. Okay, we have one more thing for today. Higher order derivatives. So this is going to be really quick. Higher order derivatives, what does that mean? Did you know it is actually possible to take the derivative of the derivative? And then you could take the derivative again of that. And then you could take the derivative of that. So you can take the derivative as many times as you want. These additional derivatives are called higher order derivatives. So any derivative that is bigger than the first derivative, so the second and the third, they would be higher order derivatives. This is how they're represented. So we say here y prime, right? And this we would call y double prime, because it's two derivatives. We call this f prime of x. This would be f double prime of x. Y'all get the idea. F triple prime would be here, y triple prime would be there. Or the third derivative, you could say the third derivative. And these are just other ways to represent those higher order derivatives. So we know this is the derivative with respect to x. This is the second derivative with respect to x. The third derivative with respect to x. Okay. So we're just going to do one higher order derivative, and then we are done with notes for the day. All right. Here is our example. Y'all don't have to have this whole table in your notes. You just need to know that there are higher order derivatives and know how to say them. So f prime, f double prime, y double prime, and so on. All right, and you do need to know this. So write down this example. And I want you to find f prime of x. So if we're finding f double prime, right here we're trying to find the second derivative. The first step is to find f prime. So first, f prime of x equals, so go ahead and find f prime of x. All right, and now I'm going to do f prime of x. So we have the 3, it multiplies out in front. Y'all, anytime you have a fraction and you're multiplying a whole number to a fraction, so the 3 turns into a whole number and it multiplies to the fraction, that's going to multiply just to the numerator. So the 3 times 3 over 2, that turns into 9 over 2, 9 halves, x squared. Then we have plus 10x minus 6. That should be what you got for the first derivative. We are trying to find the second derivative, though. We're trying to find the second derivative. So what we're going to do now is take the derivative of the derivative. So 2, we're going to say, okay, f double prime of x equals, and we're going to take the derivative of this. Take derivative of f prime to get f double prime. Okay, so go ahead and take that derivative. Tell me what you get. All right, now I'm going to take that derivative. So we're going to do the power rule. The 2 multiplies to the top. So we get 18 over 2x, because we subtract 1 from the exponent, right? Plus 10. And then the 6 is 0. The derivative of the negative 6, derivative of a constant, is 0. So there's f double prime. If you wanted to, you could simplify, but I'm not worried about simplifying right now. We just need to know how to take higher order derivatives. What if we wanted to take the third derivative? F triple prime of x. Well, you know what to do. You would just take the derivative of the second derivative. So you get the idea. I just wanted you to know you can take the derivative as many times as you would like to. So if we did this, we would just get 18 over 2. And the fourth derivative would be 0, right? Oh my gosh. I could keep going. I'm so excited. I just want to keep taking derivatives. Y'all, wait. We got to get to 0. The fourth derivative, 1, 2, 3, 4, equals the derivative of this constant, which is 0. Okay. You all get it. Higher order derivatives exist. They're a thing, and you can take them. And now you're going to practice.